you very much. Uh, so it's lovely to see a big crowd here. We've been awaiting you and keeping the program pending so that you could attend this particular talk. So also we're thankful to Mr. Satyanarayan, who has, I think, arranged for you to be here. So lovely to have you all here. And in fact, I think that let's, rather than making it just interaction where I give you just talk to you about something random and then you go away with hardly anything, we would love to make this an interaction, since you are here all through the day and your aim is to visit the exhibition here, which is called Vigyan Samagam. I think it could be very helpful if we all talk with each other and then try to spend the day in a more fruitful way. So just to introduce, I am Samir Turde from, I've come from Pune, from an institute called Inter-University Center for Astronomy and Astrophysics. Short form is IUCA. And I am a person whose background is physics, but I love studying using physics. I love studying things of the universe, not just the Earth, but otherwise as well. And therefore I can call myself an astrophysicist, right? And maybe since I don't have a background from your side, so if it would help me give this talk and do other interactions, if I know what you guys have studied till now or are studying and what do you aim to do later. So anybody who is representative, I hope all of you are of from similar background. Is that so? It's not so? Okay. So then could any of you as a representative tell me shortly about your group? Very little, brief. Maybe one of the yeah. Physics plus chemistry plus all the engineering. Okay, it's lovely. Still, so you're all from science at least. That's science and engineering. Lovely. Okay, and what is this training that you're that you're doing? It's for nuclear sciences. Okay, so yeah, I can see that there's, of course, the world started with the formation of the first nuclei, right? And in the background, actually, I was just reading a book about nuclear sciences. It's a lovely cartoon book for school children called ABC of Nuclear Physics. It's lovely how they have made it possible for children to understand all these things from right from electrons, neutrons, protons, what are their properties, their how they make up atoms, right to how fusion occurs, and rather than taking them towards bombs, they have taken them towards nuclear energy right from the beginning to the end. Lovely to see that. And how that connects with this exhibition is that this exhibition is basically an exposition to mega projects, huge projects in which India is a partner. But there's also a connecting theme. So all these projects have some or the other connection to things in the universe. Okay, not just on the Earth, but in the universe. And they are quite nicely represented by this lovely graphic, which even Satyanarayan sir had a big role to play in making. So you'll notice that this one kind of shows you a timeline of the universe, and later, I mean, it's here of course, but later also you should pay a little bit better attention to that. So it shows kind of timeline of the way we understand the universe to have evolved this world that we live in. So it kind of starts with the Big Bang, which is an expansion of the universe out of pure energy, where no matter existed. It was just densely packed pure energy in a single point. We do not understand that yet. It's still beyond our understanding, but that's why some of the projects which are towards the beginning of the timeline, it's closer to the words Big Bang, like the INO, the India-based Neutrino Observatory, and particle accelerators like the ones run by CERN, right? You must have heard of the Large Hadron Collider, which amazingly gave us predicted particles like the Higgs boson, which we had never seen, but we thought we knew enough science to predict. And then it proves us right back. because yes, if we can find them from based on the theories that we already have, then probably those theories are right. So those are the kind of projects which would delve into realms of high energy mechanisms, high energy phenomena, and also would like to observe neutrinos right from the beginning of the universe, which are actually particles which don't interact with anything, hardly interact. They are byproducts of nuclear reactions as well, right? So fission reactions, but here we are talking about the earliest universe where they would have just been formed anyway without even a reaction happening. There would have been no elements which do nuclear reactions, fission reactions. Those heavy elements were formed quite later, and that's where we will be looking at what we'll be looking at or trying to actually make with the FAIR project, the atom and ion research project facility that will be there. It's an amazing facility which is actually trying to kind of make every element that we know of inside a lab. So just imagine, I mean, it's just like a challenge. Okay, so I want to make everything from hydrogen to whatever 116 or whatever atomic element that is there in a lab. Okay, so that's quite a fair challenge. So we have that happening there, and that is actually going to will need to simulate conditions as they were in the early universe, when the original elements that we are formed of were getting made. Hydrogen was combining to become helium, helium was combining to become oxygen, carbon, nitrogen, silicon, right? And then came the first stars, which over billions of years evolved, and at their centers are conditions such that they can actually form much heavier elements. Okay, so if you ever ask yourself, where did all these elements, these particles which make up all our molecules, where did they come from, all these atoms? So many of them came from nuclear reactions inside stars. But the way we understand nuclear reactions now, particularly fusion reactions under certain conditions of stars, there is actually a study of astrophysics which deals in that, and Professor Meghnad Saha was a big contributor to that from India. So the way we understand nuclear reactions, we can't go beyond iron, because at that time nuclear fusion stops giving out energy. When fusion happens, it starts taking in energy, right? So that's something we realized as we studied nucleosynthesis as it is called. And this lovely discovery led us to actually a good understanding, and also explained some of the observations that we had in space. So the observations we had in space were through astronomy, were that we saw stars, and we saw them in various stages of life, because there are so many. So we just point a telescope in any direction, you'll either have a young star, old star, everything. We knew particularly places where stars had actually died. They had finished their life and exploded in some huge explosions called supernovae. We wondered why they had exploded, first thing. Why didn't they just continue fusing things and making other elements? But they exploded. We didn't know why. We didn't know why. When we look at that place, we see an immense amount of heavy elements in the spectrum. Spectroscopy, where we study the light coming from particularly the one emitted by molecules or ions, and then we know what ions and molecules are there at that place, because they have a characteristic frequency or wavelength of light that they emit. Other than the rest of the light, they have this particular frequency which only that kind of ion or that kind of atomic nucleus or excited elementary particle of that element releases, and through that we can know what is there. So sitting here on Earth, we can do spectroscopy of, say, gas cloud somewhere else. These gas clouds are formed of blown up stars, and we know there's hydrogen ion even, right? So we were surprised to see iron there, and then traces of other heavy elements also have been found beyond iron. So both combining nuclear research and astrophysics, we could come to the theory of the evolution of stars beyond the supernova even. Okay, and now we know that in that supernova event, conditions become beyond what could be inside a star, and those are extreme conditions where even two iron nuclei could combine to form heavier elements. So you could take an oxygen nucleus and combine it with iron to form a intermediate something. You have all these lower elements hanging around. Their nuclei could combine to form heavier nuclei, and that's where all these nuclei, that the heavier ones that we are made up of, have formed at the centers of stars or during the death of stars. And then that gave us an idea that maybe our sun is not really the first generation star, because if it was a first generation star, it would only have hydrogen and helium. Hydrogen, most of it would be hydrogen, and around it also there would only be hydrogen and helium. But it's not that. We are not made up of only hydrogen and helium. We have so many heavier elements, right? We depend on them to make ourselves. Therefore, this must have been a place of another star earlier than the sun, which exploded and which put out all these elements of what we can call life and otherwise out, and then the remaining hydrogen could combine to form another smaller star, which is now the sun, right? So that leads us to an understanding of ourselves. How are we here? How is our solar system here? Right? So that's how you see we are progressing in the timeline. We've come from the beginning of the solar system, right from that energetic age, into the forming of the first atoms, and then into that place where we started understanding stars and their clusters called galaxies. Now after that we come to an understanding of how our own star could have formed, and there and how our solar system could have formed. In fact, we are still looking at other details of our solar system by making better and better telescopes. So those are also featured in those projects that are part of this exhibition. But one particular project which is not directly related to astronomy or just observations is ITER, which does not actually look at something, but what it is trying to do is trying to replicate the reactions at the center of the sun here on the Earth, but in a controlled way. That has already been done. We have replicated reactions at the center of the sun on the Earth. Do you know where? I mean, I'm sure you do. So the sun center basically fuses hydrogen nuclei into helium nuclei, producing a lot of energy. That's right. So I mean, these are experiments, but I'm saying we've already done it. We've converted hydrogen into helium on the Earth. And hydrogen bombs, yes, we have never not been able to control them, and then the people who were making hydrogen bombs did not want to control them anyway, right? So that's the fast use of it in a wrong way. But I think that experiment is going to be one of the most important experiments in the future, for the future, where we would have, if it succeeds, we would have controlled fusion reactions giving out continuous and significant amount of energy. Okay, and I think that is one of the most important projects here. So please go to the exhibition after this and explore all these projects. There are trained volunteers ready to explain to you everything in detail. Spend the day there. I think you could spend the whole day at every booth, get as much information as you want, and maybe you could also contribute to some of these projects after you get trained properly. So, but my talk here in the next hour or so, I'm going to delve into the world of astronomy, astrophysics, and introduce you to some of the largest telescopes in the world. Okay, telescopes, the world is very exciting, and a lot of new things are happening in the world of astronomy, and we are looking forward to several big telescopes coming up in the world in the next decade. Right? So I'm going to introduce you to them, and this talk is supported by especially supported by the 30-meter telescope project. So all of us, all the projects have been given 1 week during this 2 months of this exhibition, where we present our project here, and also related information is shared with others. So that's why this talk particularly is going to be about the 30-meter telescope. If you are interested, I think the next week's talks, there's going to be give their talks every week. Okay. Fine. So when I say 30-meter telescope, does it at all amaze you or touch you at all, this name? It does to some of you. Thank you. Well, so let me actually make it a bit more relevant as to why it should excite us, this name itself. Okay, and I will not assume too much background and then directly start with a very simple explanation of what a telescope is supposed to do. Okay, I'm not assuming any background in astronomy or too much physics knowledge. So a telescope, which could be used by anyone of any age, of any gender, it actually is used to look at distant objects. Okay, so that's the aim of a telescope. The lens system, the optics as it is called, is designed in such a way that we would be able to focus light which is coming from faraway objects. Okay, and astronomers in a way are very handicapped, because our labs, our experiments, the things that we observe are extremely far away from us. They are beyond human reach. Okay, nobody can even touch the closest object like the moon, or I can't smell it or taste it or something. So we are limited in our senses to just using sight. We just use vision. Okay, we only study the light coming from these objects, and there's nothing else, hardly anything else that we can do about that. So what the aim of the telescope is to make things look bigger, brighter, and to see them in more detail. So I would say sharper, let's say. Okay, so yes, our telescope uses lens system to magnify things. The image that we get is magnified. So this is the most common thing that we know of, that as a use of a telescope. I look at faraway objects and I see those things bigger. Okay, in fact sometimes a question is asked, how far can you see with a telescope? Okay, I'll answer that a little later. So, but then that is not the only thing. I think the more important, another important thing about the telescope is the brighter part. Okay, because if we are not using a telescope just to look at birds or faraway mountains or something like that, then the telescope is mostly used at night to see objects which are there in the night sky. Okay, and these things, just imagine what all things have you seen in the sky till now? You know there are several, thousands of different kinds of things in the sky, but how many of them have you seen yourself? Have you seen, you've seen the sun and moon, of course. You've seen stars. In the cities, we hardly see any stars these days. It's maybe if you look up, maybe 10 stars. Okay, but our naked eye's limit at a properly dark place, a naked eye's limit allows us to see at one time around 2,500 stars in the sky. Okay, if you just go to a village outside Mumbai maybe and look up at the night sky, you should be able to count up to 2,000 stars easily, and then if you go to the limits, 2,500 even. Yeah, so those are all missing. Yeah, because most of them are faint. You can only see the brightest ones from the cities because there's so much ambient light around. And just after that, just forget about the other things like, suppose planets, faraway planets. Brighter planets can be seen. And in fact, there's a bright planet Jupiter in the sky these days. So if you're interested, you could look at the eastern horizon around 8 p.m. or so. You would see a bright star-like thing there, and that would be Jupiter. Okay, so those things are visible, planets are visible, stars are visible. But if you say, I want to see Pluto, or you want to see something called the Orion Nebula, okay, or you want to see the closest galaxy or faraway galaxies, all these would not be visible because the light from them is very faint. Okay, some of these become visible. Even our own galaxy has a lot of place in the sky, but we can't see it. It's called the Milky Way, and the name is Milky Way because when it was named, there were times when there was hardly any electricity and people would look at the sky, and the sky it would look like a path, like a road which was milk, like washed with milk even. So it is that bright at that time, and that's why we would call it Milky Way. It's not that its brightness has gone down, our brightness has gone up, so we hardly see it. So all these faint things are not seen, and that is why we need a tool to make things look brighter. Okay, that's why the brighter is also pretty relevant. And what a telescope does is it increases the area of collection of light. How come? So you see the last sentence compares all these things to the eye. So basically a tool needs to enhance my vision, right? So it's like machines enhance our capacities. This tool enhances our vision. So our eyes, if you note it, they have the iris would have a diameter of around 1 centimeter or even less, and that's our collector of light. However, this telescope allows us with its optic system to use a bigger area to collect light, and then the light gets focused. Okay, so I'll just take you to a quick view graphic in which a simple type of telescope is shown. This is called a refracting telescope, and it uses the phenomenon of refraction of light. So light, if it's coming in parallel rays from far off, that's what objects at infinity do. The light coming from them seems to be parallel. So the lens actually changes its direction by refraction, and it focuses it to a point. Okay, so that's the distance between here to that point is called focal length. All this is part of your optics study. Okay, so you see, if I had a bigger lens than this, it could collect light over a bigger area. Okay, and what is it finally doing? It is collecting and giving me at a point, right? So whether it's my eye lens or a bigger lens or even a bigger lens, the difference is that they are using bigger and bigger area to collect the light, right? They are like funnels. Use a small funnel or bigger funnel, the amount of let's say if you are collecting rainwater, right, the amount of water collected by a smaller funnel will be less than a bigger funnel. So these are kind of funnels which collect light. And that's not all, because you see, when I collect light to a point, it does not give me an image, it gives me a point. So all the light coming onto the lens is concentrated at a point. I cannot make sense of that point, right? So then I have to reverse that process and make that light in such a way that my eyes can also see it now. Okay, so it's more light, but it's now has to become parallel rays, because my eye also has a lens. Then that will concentrate the light onto my retina. So we need this particular system called the eyepiece, okay, which basically changes this this light will of course continue going. It will not stop at the focus, it will keep going. So what it does is it changes the direction of the light from this diverging out like that to something which is parallel, and then which can be then absorbed by my eye. So what I've done is I've collected a lot of light, and then with this lens I have changed that light to a smaller beam suitable for my eye. Now I can put my eye and see, or instead of my eye I could put a camera here and take pictures. Okay, so that's the advantage your telescope has given. It has given you a bigger area, making things a little brighter. However, we also notice that from optics, if we know the focal length of this lens and if we know the focal length of this lens, we actually can manipulate these two to give you a magnified image. The image is also magnified by the use of proper lenses, so that the light that you will get here will not only carry information just in terms of light, but it will also give you a magnified picture of that, right? And in physics, I don't want to get into that much advanced level things, but if you know the wavelength of the light that you're collecting, okay, and a certain kind of aperture is given to you through which the light will go, right? The sharpness, the details that you get of the image are dependent on the diameter. Okay, so the bigger the diameter, the sharper your images will be. It's called resolution, if any of you have come across that. So the resolution is dependent on the size. So that's the third point. makes images sharper. Because just having a big image which is very bright but fuzzy doesn't make any sense. I have to have a sharp image. So this, what I'm showing you, is something which people like Galileo 400 years ago had used and started looking at the sky, right? So these were refracting telescopes, and over the time people realized that making these lenses was becoming more and more difficult. Bigger and bigger lenses were becoming more and more difficult to produce. Why? Because lenses need to be made out of very good glass. They need to be perfect. I'm sure those who are those who would get into instrumentation or need any kind of optics would realize that how costly optics gets when you go for precision instruments. Why? Because the glass has to be perfect. It should be totally transparent, should not have any impurities inside it, should have perfect curvature, right? And should be smooth. It should not give aberrations, right? So making lenses bigger and bigger is very difficult, and you'll notice even in daily life we don't see lenses so often. But what somebody else realized is that we do see something else which can act, which can do the same thing that this lens is supposed to do. The parallel light only needs to be concentrated to a point by this lens. This lens is playing no other role, you see, right? So this lens contributes only the role of focusing the light to a point, right? Changing the direction and focusing it, and of course the focal length matters. But I think there's another thing which can do the same role without having the light passing through it, okay? And that is a reflector, that is a mirror, okay? And mirrors can be made really big. So of course there was a gentleman right around 50 years after Galileo started using his lens telescope. He came up with this idea of using a concave mirror. You see here there's a concave mirror, light is coming like this onto the concave mirror, and concave mirrors can actually focus light inwards towards the focus, right? So that's what he started using, and here the light doesn't have to go through the glass, so it could be thin, it could be just a thin sheet, but it has to be perfectly curved. That has to be taken care of. If you do that, you get rid of all the other requirements like clarity, opacity, colors, and all these things. There's no chromatic aberration in a reflection from a glass, right? And it could be front coated glass, so you don't even need to have it at the back. The mirrors that you use while brushing your teeth are coated at the back, but this is coated in the front. So you can put, he was using a layer of silver on that, right? You could do some electrolysis and then deposit a layer of silver onto a glass plate, right? These days we put aluminium vapor. We just expose it to aluminium vapor in a vacuum chamber, and it just deposits a tiny layer of aluminium on it. So this one changes direction of the light and it goes in this direction, right? But yes, of course there's a practical difficulty that if you now put your head here to see it or your eyepiece here, it will stop all the light coming from this side. So the ingenious way was to just put a small, not as big as the diameter of the tube, but a smaller flat mirror, and just change the direction of this by 90 degrees. Okay, so the light would have been going in this direction, but it changes to this direction, and you make a hole in the tube of the telescope and just see it here, add the eyepiece here. Okay, so the focal length is now from here to here, right? Everything else is the same. There's a focal length, it gives you magnification, the light is collected on a bigger area and focused, but we are just using a concave mirror. Yes. I just said, yeah, it is done in vacuum chambers. The coating is done in vacuum chambers. All vapor deposition needs to have vacuum. But you'll just realize the challenge when I come to large telescopes slowly. So this is called a Newtonian telescope, in which we are using reflectors instead of reflection instead of refraction. Okay, makes things easier, and then we could make bigger and bigger telescope. People also said, this is a little inconvenient to me because I have to see from the side when the object is on this side. So let's say I want to see in that direction. Then my telescope is like this, let's say, and I have to look like this, right? According to this, I have to see here if the object is there. Well, that's an inconvenience if you want to see birds or whatever earthly life. But if you want to see up, I particularly find it very convenient to have a particular perpendicular eyepiece, because I cannot spend my whole night looking like this. My neck will go, right? So I particularly like, if things are above, I like looking at them like this. So that's convenient, and therefore most of the amateur astronomers who are not professionals but just love looking at the sky for a long time, actually use their eyes to see things through the telescope. They love this telescope. It's a Newtonian telescope. In fact, this prop that we have here is a Newtonian telescope. The diameter of this one is 6 inches. So the mirror, the diameter of it is 6 inches. Okay, and when we talk about telescopes, ahead of these slides, I'll be talking about sizes of telescopes, and in that I'll be referring to the diameters of their primary. Okay, so primary is the first element which interacts with the light. The first one had a lens, here it's a mirror. Okay, so whenever I talk about large telescopes, including the 30-meter telescope, I'm just talking about the diameter of the primary. Okay, so now if you are imagining the whole telescope to be 30 meters wide, or 30 meters in like one dimension, don't be fooled by that. There is more to a telescope than just the primary, right? Because you see this, if this is the primary, the telescope is much bigger than that, right? So we're just talking about the essential primary diameter right now. Some people said, okay, Newtonian is fine for amateur astronomers, but if I want to make bigger telescopes, I would need something more convenient. So they made a concave mirror with a hole in between, at the hole at the center, and they put another mirror here. These can be changed depending on various people have tried concave mirrors, convex mirrors, flat mirrors, right? And they have come up with various designs. But what we're essentially doing is, instead of putting light in this direction, we're putting the light back in here through the hole here. Okay, and then put the eyepiece here or camera or whatever, right? So this is another kind of telescope. This particular one, which uses a concave mirror, is called the Cassegrain, but there are other Richie Creton and others which use flat mirrors as well, right? So it depends on the kind of technology that you want to use. This basically allows me to fold light. See, the focal length, if there was a lens here, the focus would have been here somewhere. Okay, long focus, and then there would have been the eyepiece focus and would have made the telescope really long. Here it's the light was going in this direction, it goes in this direction, comes back here. It's like folding up things, right? So therefore it also makes the telescope compact. Okay, so after all this background, let me take you to a real telescope, picture or show you some telescopes of the world, and there you will realize the importance of all these things that I said. Okay, so that was background physics from your optics class. Let's now get to the real world. Ready? You have a question? No. Okay. So I'll be making this presentation a little bit of fun by talking to you about the world's biggest, largest, widest, things which amount to records, because we all love those kinds of exciting things. Right? Who cares about average? So the world's largest refractor. Okay, the first refractor used by us was about 2 inches in diameter. That was Galileo, and you can see obviously we have something bigger, and this is something regularly used by amateur astronomers these days. Even if you any of you have interest in astronomy and want to buy such a telescope, these are available off the shelf on the website, on websites even, I mean on the internet even. But things like these you cannot buy. Right, just see, directly go to the last line and see the diameter. 40 inches, 102 centimeters, that's a meter, right? A lens, so it has a lens which is 1 meter in width. Just imagine it's like it's this big, the whole length. It's a circle which is 1 meter in a little less maybe. So it's a 1 meter lens. I myself never seen such a lens, such a big lens. I've seen smaller, but not that big. Okay, and that is just the lens. And this is a blueprint design of the telescope. It was made in the 1800s, 1880s, I think. So and then in that you can see this tube is the telescope. This is its stand, okay, on which it's called the mount. Okay, and there's a support base here, and it is covered by a dome so that it keeps the atmosphere out. You notice the diameter of this would be 1 meter approximately. It's a little bit bigger maybe, right? And then compare that with the whole tube, because the focal length is that much, and then you have the eyepieces here. Okay, so the tube itself becomes 20 meters big, almost 15-20 meters, right? So, but I will not call this a 20-meter telescope. I'll call this 1 meter telescope because its diameter is that much. And this whole thing has to be kept steady and all that. So you can see a staircase going up, so that if there's some repair needed here. And then it's a difficult thing to reach the dome. But where do you think the person will stand to see from this? Because this building is almost like it's a 1, 2, 3, 4, 5-story building. Where do you think the astronomer will stand? Yeah, here. Okay. Now I want to see if they want to see the object here, but I want to see an object here. Just turn this around, and the telescope eyepiece goes here. Now where will they stand? Or if they want to go here or here or here, or even if they want to turn it down here, so the telescope will go here. Now they can't change their height. They can't fly around with jet boosters or something like that. So they were ingenious things made. They would actually. So what you see here is this is a floor, but it is a movable platform. So it was a platform with hydraulic presses, and there would be steam engines running them, and you could have to actually press a button, and it would go along as the telescope moved. The platform would move up and down, and the people would walk around on it. Amazing things, amazing challenges they had back in the 1800s, and that was all done to use this largest refractor telescope. Okay, but as I said, there are other telescopes in the world, and the large refractor, I mean further bigger refractors were not made after those times, and they stopped there. So you can imagine how cumbersome it became, and that's why now all the big telescopes that we'll be talking about would be reflecting telescopes, reflectors, because they can be made really big. And how big? Let's compare some of the existing telescopes and some of the planned telescopes diameters. So in this you'll see these patches, which are actually representatives of mirrors of optics of telescopes, primaries of telescopes. And in this, the Yucks observatory, which you just saw, the 40-inch refractor, is represented by this dot. That's 1 meter for you, okay, for scale. So if that biggest refractor was this tiny dot, then these are the other telescopes of the world which have some some meaning, they are doing observations, right? So after that was in 1893 when this was made. After that we realized we need something bigger. So 40-inch was there. We said let's take a bigger step and make a reflector, but so a nice number would be 100 inches. Okay. So that would be around 2.5 times bigger than that, so 2.5 meters, a huge telescope for that era, 100-inch telescope, and it was made at Mount Wilson, California in 1917. That happened to be a groundbreaking, a path-breaking leap. Okay, although that was one of the first big telescopes, that was the only big telescope at that time. So all the great discoveries which could be made by such size telescopes were already made at that time, including the discoveries by a famous scientist called Hubble. You must have heard of this name, Hubble, from the Hubble Space Telescope. So that is named to honor Edwin Hubble, who did all his path breaking observations with this telescope, the Hooker telescope, 100-inch in diameter. Okay, but he realized, and other scientists who were using it realized, at that time he was not so famous because he was just one of the observers. So all the other scientists realized, okay, fine, now we made a lot of discoveries. What's the next step? So they made a 200-inch, just a next step, at Mount Palomar in California. Both of these exist and are used for observations even now. But that was beginning of last century, in middle of last century, we got the Hale Telescope. But this one was made with that design in which there was a hole at the center, okay, of the mirror, primary mirror. And after that, most telescopes that you will notice have had that kind of hole in the center, okay, smaller or bigger, but they have been holes, except these two, which I will describe later. So so that was not enough for people, but they wanted to make bigger telescopes. Okay, so 1950s, 60s, they said, oh, now I need a bigger telescope. What do I do? Said, let's take the next step. This was already 5 meters. What is the next step? Let's make 10 meters. Okay, and then came a challenge, a practical challenge, which always tests our limits. How do you make a glass piece, single glass piece? And in this one, it's not a, I mean, it was a challenge to make a lens big because it used a lot of glass. Now here I have to make a glass piece which is a single piece 10 meters big. Okay, 10 meters would be from here till the end of the auditorium. Single piece without breaking it. And how do you transport it to the observatory? Okay, how do you make sure that every part of it from here till there, okay, is perfectly polished, perfectly curved? Yeah. So a big challenge, and we could, I mean, I'm amazed that people actually took up telescopes like 200 inches. Even that is a challenge. 5 meter big chunk of glass, single glass, polished to that level. Polished as in it's to be made smooth, because it should not scatter off light. It should actually reflect in the particular direction we want, right? So we have to have the surface so smooth that it should at least be the 1/4 of the minutest distortion or scattering surface on it should be 1/4 the size of the wavelength that we are using, and we are using optical light. So we're talking about nanometers. So if it was 1 nanometer wavelength, it should be 1/4 of a nanometer. They should the what should I say? Sorry, the irregularities on it should not be bigger than 1 nanometer. Let's say. Amazing polishing is required, and how you could not make them a single piece. So again the next idea came up, and it was successfully implemented in the Keck telescopes. Okay, and what we did was we said there is no need for a circular glass, right? It should be a mirror which gives me big area. It could be square or rectangle, I don't care, but it's preferably a circle is better to accommodate inside in a glass, and it gives me a better area per the shape. So close to a circle, what they said is, let's make hexagons and design the complete mirror as a hexagon, and then what we'll do is we'll make small boundaries inside it and make smaller pieces of that separately. Okay, so right in the design phase they say, okay, this piece will have that kind of curvature, this piece will have that kind of curvature, this piece will have that kind of curvature, and then we make them separately, each of them properly polished, etc., and then we transport them all there. They'll be numbered, of course, and then we put them together to form this jigsaw puzzle kind of shape, and we have a complete mirror. Of course it looks like it is cracked in between, but those cracks don't contribute to my light. Okay, they just don't contribute to my light. That's all. But I have a 10 meter area, I mean 10 meter diameter, and the complete area, in that a minor line will not affect. That's what I have to ensure, so that there are no irregularities at those edges. Other than that, most of the telescope will be reflecting light, and I don't care about those small gaps. That was done, and actually it worked, and we had a telescope designed like that. This was one of the first telescopes to use this technology called multi-segmented mirror technology, a revolutionary technology, and the 30-meter telescope also has this. Okay, just note that. This is the 30-meter telescope which is being planned, and it has similar technology being used with hexagons. Okay, However, there are not these only small number of hexagons. There are almost 500 pieces. Okay, and the various concentric rings here have different curvatures. So they have to be all made separately at separate places, and some company has to actually take up that job and give us this finished product. Okay. So Keck telescopes were one of the successes of the multi-segmented technology, and then we had other telescopes using the similar ones. But then there are other people who dared and said, okay, we will make bigger telescopes. So there are telescopes called Gemini and Subaru, which have mirrors which are about 8 meters in size and single piece. Okay, so yeah, that's there. And in this, at the bottom, you'll notice Hubble Space Telescope, which we are very proud of and say this is the best telescope in the world. But these telescopes exist. So you can't really say that it is the largest or even part of the largest, but in space it is the only one. So in space it is the largest kind of, and its diameter is around 2 meters in size. The advantage there is no atmosphere, no human intervention, no city lights, nothing else to stop it from seeing the image at its purest, clearest level. On the Earth, we have to accommodate all these factors, and therefore a bigger size is required. Okay. And now we are going to plan telescopes like the 30-meter telescope and even the European extremely large telescope, which become comparable in sizes to tennis courts and basketball courts. Any of you have those sports as your favorite? You can imagine now, every time you see a tennis court, you'll see a huge telescope there. All right. So, sorry? No, it's a planned one. In fact, again, we do not have a spacecraft big enough to deliver a 6-meter telescope in space. So they had to make mirrors, fold them on top of each other and send them there. Because there they cannot send them separately and have a mission to join them together. Now they have folded them on top of each other. It is supposed to go out there and then unfurl like a flower. So every bit has to work properly. Every bit of hydraulics, electronics, everything has to work properly. So hopefully it will be up and it will unfurl and give us good images soon. I'm sorry? Those kinds of facts I don't have readily available, but I think that is easily found on Wikipedia. Yes. This hole? This big telescope? Yeah, it is to use that just a moment. So I showed you this one, right? So here you fold the light this way and then send it back through it so that your cameras could be here. So that's the hole. The primary has a hole so that light, instead of having to go on in some other direction, can go right through in the same direction. Right? So I'm pointing the telescope this way and I'm also looking at it this way. Right? Okay. Yeah, let's clear doubts. No, there should not be simple doubts. I'll come to that. Please have some patience. Okay. So now we are coming to other telescopes. Now these are reflectors, and you'll realize what kind of steps we have come from the largest refractor. This is the one that has the largest used area. Okay, it is called the Grand Telescope of Canarias, which just means the Grand Telescope on the Canary Islands, which are in Spain, and the diameter is around 10.4 meters. Okay, so the mirror itself would be almost size of this room, and we have very good experience with 10-meter telescopes now, because there are so many in the world which have around the same size. Excuse me. So this used to be my hero telescope when I was in school, the Keck Telescopes. In fact, they designed this for the first time and had a success, and they said, "Ab design ready hai to ek ke jagah do bana lo," because design is the most expensive part. right? Once you prototype anything, you can just make copies of it. So they made two, and they put them together. They're still active. Each of them can work separately, but there have also been experiments to interfere their light and get even better resolution from the stars. So that's a very pioneering telescope and respected by most people, almost all astronomers. So then there are another set of important telescopes which are called the Very Large Telescope. We are very imaginative in naming telescopes, and this is called the Very Large Telescope. It has 4 units, each with 8.2 meter diameter. Just look at the picture, you'll notice something special. So this is, of course, sorry. Yeah. So the lines here are, of course, drawn by computer graphics, but these telescopes do exist like this. They are like that, and these are some hills and mountains. And what you see here is not the ocean or sea. It is clouds, because we have to make telescope sites at we make telescope sites at a good altitude so that they're not disturbed by the regular everyday clouds. Okay, if we had skies like Mumbai, we would only have, let's say, 50 nights every year which would be clear. Right? We need to have 200 nights every year. Some things we cannot control. If there's a storm, if there's a rainy season, we cannot control that. But we need to get the largest number of clear nights to observe the sky. If we are making a $1 billion observatory there, right? So yes, this is a site which is above what is called an inversion layer, and those low-lying clouds which can cover cities and towns don't affect these observatories. We also have the largest binocular in the world, which is called the Large Binocular Telescope, made out of 2 elements, but they are both looking in the same direction. They have to look in the same direction. That's the compulsion here. And of course, these are all there. These can look in separate directions, but this one is made so that we try to do something called parallax experiments with close by stars, where distance measurement is done by looking at it from here and then here. Okay, so this is a parallax experiment. This is the world's largest binocular. And then there are also telescopes which look at the sun. Okay, like the McMath-Pierce telescope actually uses 1.5 meter sized primary to reflect the light of the sun. But the primary is big in this case to get resolution, to get a sharper image, rather than to increase the amount of light we need. We don't need to increase the sun's light, right? Anybody who has tried to burn a paper with a magnifying glass? We don't need to increase it any further. In fact, the challenge here is to reduce the sun's light, because the 1 meter size mirror collects around 1 million times more light than your eyes would, right, or more. And that has to be cut down 99%, so that person there doesn't get burnt or something. So it's a different kind of challenge, but the diameter there is more for increasing the resolution, the sharpness of the pictures. Okay. We also have Southern African Large Telescope, which has the largest mirror dimensions. They will do anything to get a record. You see, somebody says मेरा ज़्यादा area ज़्यादा है, ये बोलते हैं नहीं मेरा dimension ज़्यादा है. Okay. So the diameter is 11 meters on one side and 9.8 on the other side, right? So no, that's not the reason. Of course, they didn't want a record. It's a functional requirement, and this telescope is such a telescope which does not have the capacity to move around and look in various directions. It just looks in one direction. Okay, and so it's called a transit telescope. So what it does is it uses the Earth's rotation to allow different objects to come into its view and observe them, right? So that limits the area that it can see in the sky, but then that reduces the cost many times. Okay, so you've got a 11 meter class telescope looking at the sky, and the 11 is important because we want to cover as much as patch of the sky in this direction rather than in this direction, right? So the coverage is required here because it's, let's say it's looking in this direction. The Earth moves like this. Okay. So this point will definitely come here sometimes and then move on, but that point will never come up. because the sky moves from east to west, right? So the north-south dimension is more compared to the east-west dimension, right? So that's why they have the largest dimension rather than for a record. Okay, this is in Sutherland, South Africa, and important thing, India is a partner in this. So India has a, I think, 11% partnership in this, and so at this kind of size, it becomes difficult for a single country or even a single institute or even for a single country to afford such a telescope, such a project. So people put in together money and brains and make such ingenious things. So Indian scientists, Indian astronomers have a stake in that, and they get 11% reserved time for observation from whatever time is approximately calculated. Let's say we have 200 nights, so we'll get that many nights every year. Okay, so now these are the largest telescopes which exist, but of course there are others being planned and constructed, and construction itself, the making of a telescope itself is a big deal. So I just missed this. So yeah, this is actually a twin of the Southern African Large Telescope. It's called the Hubble Telescope in Texas, USA. It has very similar design and used in a similar way. And just to see inside, that's how the mirror looks. So you see, it's long in this side and short on this side, right? And now maybe you'll get since this is a real picture, you'll get a approximate idea of the size by the people who are standing here. There are two people standing here discussing some details. Okay, so each of these segments is close to the height of one person, and then they are pieced together and they form a nice proper curvature that we want. This one doesn't need to have a hole here because it's got cameras up there instead of at the back side. Okay. All right, so those are the big telescopes that we have, and I was saying that the construction of these is also a very challenging process, and we include people from all sorts of branches, including let's say engineering. We need mechanical, civil, electrical, software, all sorts of engineers. There have to be astronomers, of course, who will give us the science goals, what will we observe with the telescope. Then there are several other physicists, meteorologists, even geologists who contribute to the making of a large telescope. So usually let's say take the example picture of the construction of the very large telescope. I showed you that it is on top of a mountain and it's quite high, right? And there people had to actually I mean, this is a construction picture, so what the people had to do is to find a place which is really far away from the closest town. In fact, so far away that they found a place 700 kilometers away from the closest town or city, right? In fact, this telescope, not this telescope, but its hostel, which is close by down here, was in fact featured in a James Bond movie, Quantum of Solace. Has anybody seen that? So if you haven't, then go see it again. So the last fight which happens is shot here. Okay, of course the house there gets destroyed. It doesn't get destroyed in real. That's all CGI. But it was shot here. And in that movie, it's basically it's to be shot in a desert. So it's shot in a desert around here, and you can't find anything close by to the observatory. So everything has to be self-contained here. So at such a remote place, you need to go there. You first have to find a place. You have to make a road to every place that you visit for a site survey. You find the perfect place, and you already have a road to that. Then you start making the land useful for construction. So flatten it up, start having some equipment moved there. You start construction of the primary base of the telescope. Then you put on the enclosure. The structure of the enclosure, you complete the enclosure. This is usually a dome structure. And then you move in the telescope pieces and then assemble it inside it so that dust doesn't settle on it while doing that. Okay, and then with these kinds of steps, you come across a finished telescope like this. So that was a cartoon sequence of construction, and which is going into the planning of the largest planned telescope on Earth, which is going to be the European Extremely Large Telescope. Okay, this is again at a site close to the Very Large Telescope. Okay, again very extremely innovative naming. Yeah. The Paranal, Chile is that site, and the diameter of this is going to be close to 40 meters. Okay, it's a huge telescope, and if you're still not able to understand the hugeness of it, look at this graphic. So it compares it with a aircraft which could actually easily, two of them could easily go inside this and stay there. Okay, it's going to be huge, but the rewards are also going to be equally big. And of course, that brings me to the 30-meter telescope. It's not 40 meters, but it's 30 meters. So, but then this telescope is in Chile, Chile, which is in the southern hemisphere, and the 30-meter telescope is going to be on the islands of Mauna Kea, Hawaii, in the United States, which is in the northern hemisphere. So we'll be looking at different parts of the sky. Both these telescopes will be looking at different parts of the sky. Southern hemisphere and northern hemisphere have some overlap, but they also have things which are separate. The diameter would be 30 meters, and of course the main reason why I'm talking to you about this telescope so many times is because India is a partner in it. Right? India is a partnership, a part of the partnership, and this is one of the unique projects where I think India and China work together along with Japan, Canada, and the universities of California in the USA. So all these people work together and they contribute to the telescope. It is going to be made at this really what I call is a sacred location, not just sacred for the traditional people on that island who respect it as a place where the mother goddess lives, at top of this huge mountain called Mauna Kea. It's actually an extinct volcano. So the explosion of this volcano caused this island to form at some point of time, thousands or even millions of years ago. It's been extinct for a long time, but you'll notice it also makes a unique environment. There's a person surfing here, the beach here somewhere, nice waters, and then you just climb up. It's a 4 kilometers above sea level. Amazing. Just see, Mount Everest is 8 kilometers or so, and this is half that height. Okay. And it's on an island. It's just one thing. From here, sea level 4 kilometers above sea level, and up here you can see snow-capped peaks and sea beach. Just imagine, it's such a wonder of nature. And the top of this, since it's so high, we can easily build things. We can easily find conditions which are suitable for observatories. And so this happens to be the best site in the world for astronomy. So it's sacred for the people, but sacred also for astronomers who have already built 13 international telescopes there, like including the Keck Telescope. So it's giving way. Okay. So these are the two domes of the Keck Telescope, and there are other telescopes on top of this. And you can see this sea here. These clouds are below that, right? So that's one of the best places in the world to build it. Build the next best observatory in the world, and that is going to be the 30-meter telescope. As I said, India has a big partnership in that, and we are contributing to making so many of those mirror segments and also the support system of the mirror segments. We are also contributing to the complete software of the observatory control system and the telescope control system. I am not going into too much details about what are the contributions, etc., because that is what you will find out at the exhibition. There's a pavilion and 10 posters explaining what the telescope will see, what will be the parts of it. You can see inside there's a big blow up of the telescope, and also some of the technologies that are being developed in India, who is developing them, etc. So please go and have a look at the pavilion for extra details of this. Now, we are just going through with the theme of the large telescopes, and I was telling you that I will more tell you about the technologies used, etc., so that you appreciate other things easily at the pavilion. So this is the best site in the world, and of course Paranal, Chile is another great site where the other big telescopes are coming up, but it's got slightly lower in height and it's got some issues, because of which it becomes the second best. Okay. However, you'll notice that whatever the site, you'll always these days in modern telescopes, large telescopes, you'll notice this. There's something weird here in this picture. Who can who can point that? Maybe next picture will give you a hint. There's light coming out of the telescope instead of going inside it, right? There's a laser beam, and is there anything common between the other picture and this picture? In context to the laser itself? Yes, it's a yellow laser. So it's not like this green laser which I was using, which unfortunately the battery has gone down, and or we use red lasers, etc. Have you ever used a yellow laser? Okay. Because, but if you had a use for it, you would. Right? If you had requirement, you would. So why are we using a red laser? The green lasers are probably yellow laser. Green lasers are probably easier to make and cheaper. Well, that is because we want to use it for a particular purpose, and that is called adaptive optics. Now, this technology basically allows you to, as I like to put it, take the twinkle twinkle of that out of that little star. Twinkling is something which is very romantic or whatever, fascinating to little children even, and we look at, when we talk about stars, we talk about twinkling, which is good for some people, is bad for others. So astronomers don't want them twinkling at all. Why? Because twinkling is actually an artifact. It's caused by the atmosphere wiggling around, right? So atmosphere is like a large lens, but it wiggles around all the time because there are turbulences, and it causes, let's say, the image of a star, which would be a point image, or if you're out there in space, if you take a picture of it, it would be a point, right? So that point image, while the beam is traveling to you, it is being focused because of this atmospheric disturbances. It's sometimes focused at one point, it's sometimes focused at another, and changes rapidly. Okay, and your eyes cannot sense that, because that rapidity, your eyes cannot change that rapidly. So what they see is a twinkling. Okay, but what is actually happening is the star is getting imaged at one point, and the next moment it is at another, next moment it is at another. So it's actually, the image is moving around, right? And your eyes see it as twinkling. Right? I don't want an image which is moving around, right? You want to take a selfie with your friend, you don't want them moving their head or dancing around if it's low light, right? And you know how bad the images are if you go to a disco or to a party which has low light. They're all blurry. Do you want pictures like that with a $1 billion telescope? No. So what we do, we would tell our friend, stop dancing. Pose, I'll take a picture. We can't do that to the star. So what we do is, let's see if this example works properly. What if that person has a particular kind of dance, okay, or if I know they are moving their head like this, I could move my camera with them, right? Or I can attach their my camera with their face, and then it would move like that, and it would be a still image, maybe just hypothetically trying to do that. So you keep thinking of on these lines and try to come up with ideas. What do I do to stop that star moving? Yeah. So finally, what people said is that, okay, if the atmosphere is changing its let's say focal length because of disturbances, what I can do is I can change the focal length of my telescope accordingly, so that the light is always focused at one point, right? So I change either my focal point or focal length of it fast enough to account for the change in the atmosphere. Okay, so that's why I said if you knew the dance, then you could try to at least not get a blurry image by moving your camera accordingly. So what is being done here is, we have to of course know what this dance is like. What is the next change which is going to be there? Okay, or what is the change which has just happened, at least, right, to counter that. So to know that change, we have to have a man-made thing there, man-made something. If I make it, I know all its characteristics. So this laser is actually used, I don't know if it's mentioned here, yeah. So yeah, so the telescope quality is limited by the atmosphere. So what we do is, we shoot this laser up into the sky, not to the stars, but to a particular layer in the upper atmosphere, which is composed of sodium ions. This comes because we have partnered with meteorologists who have told us that okay, there are various kinds of layers in the ionosphere. There's a layer of sodium ions, okay, and if I want a star, let's say artificial star in the sky, I could actually produce a star by exposing these sodium ions to a sodium light. I mean the light which is what they will absorb and give back, okay, of that particular frequency. You know of sodium doublets, which are used even in sodium lamps on the streets. So this laser is actually a very special laser tuned to that particular frequency, okay, and there was a whole lot of research which went into making sodium laser. It's quite a important development, particularly for astronomy. And so we shoot this sodium laser there, and the laser is tiny and of a particular frequency, so it goes and hits a small patch of this sodium ions. They light up and they give us an artificial star. Now I know where this is supposed to be because I'm shooting a laser at that point in the sky, right? I know where it's supposed to be. Now I take a picture and I see that it is not at the point I expected. Let's say I expect it to be at the exact center, but it's a few pixels on the other side or this side or up or down, right? Now I can sense that, and what I can do is in real time, okay, because computers have become very fast now and electronics is very fast, so in real time a signal is sent to the portions of the mirror. You see the segments of the mirror. The mirror has parts. Now therefore if I can move the segments separately, right? These segments are actually moved tilted accordingly to correct for that, right? And then therefore the light gets focused at this same point by the whole mirror together. It comes to the correct point, okay. This is called adaptive optics. We adapt to that and we use a artificial star to do this, okay. I mean if you're not convinced, we can explore that more, but then this is something which is being used. But then you'll notice that I have to actually make a system now to move the whole mirror, okay, all the mirror segments, right? And these are being this kind of technology is being used in this telescope. So adaptive optics is being put into the 30-meter telescope right from the beginning. Earlier when it was devised, people had other telescopes already existing and then they tried to put it there artificially, but this is being made with the adaptive optics technology, and India is a big contributor to this technology, and we are in fact making things which do these corrections robotically, and this technology is being used by other telescopes. So we are of course partner in 30-meter telescope. So the parts which will actually change the placement of the mirrors are being made in India, designed in India and made in India, okay. And these actuators, as they are called, they can actually give a movement to each segment up to an error of 4 nanometers. So they can make small movements as small as 4 nanometers. So imagine there's a glass block 1.4 meters in diameter and you are able to move only one side of it by 4 nanometers up or down. Yeah. Or you can use you can tilt that side by 16 nanometers and 8 nanometers on this side, so something like that, right? So that's amazing that we have been able to do that, and all these things have been designed and developed in India, and we'll be contributing that to the final telescope. And what is the kind of advantage that we expect from this? So suppose you are getting such kind of an image because of the blurring by the atmosphere, you might just, it's an actual simulation, you might just end up having images as clear as that. Okay. You would love that, right? So that's the power of adaptive optics, and it could really sharpen up images. And if we are to study things like tiny galaxies far away in the universe, I'll just show you a picture. Let's say so that was the planet. So what we will be doing with the 30-meter telescope is looking at objects which are close by. So these could be planets and satellites of planets within our own solar system. We might even discover a new planet or some other important bodies. But we'll also look at stars, other stars which have planets, and also try to find out details of those planets. Okay. Just you don't have to read all of these, but then if you notice this picture, anybody knows what this picture is about? Yes, Star Wars. So the planet Tatooine from Star Wars, it had two suns. It was a very lovely thing done with the same shot of it was a shot of the sunset on Earth, and it's nicely stitched together by George Lucas to make this scene. But we don't have to have CGI. There are planets in our galaxy itself which have two stars around which they go. Okay, and they would have sunsets like this without any CGI in real. Okay, so we would probably want to study such stars and see how the young planets formed, or how many are there, are they Earth-like, do they have atmospheres, do they have Earth-like atmospheres, leading to answer to a question whether there can be life elsewhere. Okay, that's not the exact goal, and we would like to look at even faraway things, galaxies. This is a picture, amazing picture by the Hubble Space Telescope, and what it pictures in this, captures in this picture is just one star. This is the only star in this photograph. All the other tiny points of light that you see are galaxies. Each of them would have anywhere from 10 to 100 billion stars. Right? So galaxies are there in multitudes. So as we use bigger and bigger telescopes, we actually see smaller and smaller areas in the sky. Our ability to see bigger areas reduces, but we can see them much better, each tiny area. Okay, so this tiny area contains thousands of galaxies, right? But there are still challenges left. You say, okay, everything has been achieved. We have seen the farthest galaxies, and thousands of galaxies have been captured. But no, I say, okay, no, I want to study these blue galaxies which look bigger. I want to see them better. And I also want to study these tiny faint patches which I have put some red circles around. Right? I want to see them like the blue squares. So if you have that kind of aspiration, you'll probably need bigger and better telescopes like the 30-meter one to look forward to in the next decade to give you better images. So I think that kind of covers what large telescopes exist in the world, and what are the purposes of the planned large telescopes, including the 30-meter telescope. So with this, I will finish my talk. Thank you for being a nice, patient and intelligent audience. If you have any questions, I am ready to take them, answer them as much as possible. If you want details about the 30-meter telescope itself, I would recommend going to the pavilion, the exhibition, and having a look at the posters. But anything else related to astronomy, slightly other than like what are black holes?